Hey everyone, welcome back to the channel. Today we are going to talk about something essential in machine learning, that is cross-validation. This is the method that can turn a good model into a great one by making sure it's reliable and doesn't just perform well on specific data. So let's just dive in. Here's the roadmap for today. We'll start by understanding what cross-validation is, followed by why we need it and how it works. Then we will explore the types of cross-validation and look at each use cases. We will also cover the benefits of cross-validation and then we'll discuss its limitation and finally implement everything in Python. So let's break down each part one by one. So what exactly is cross-validation? Cross-validation is a technique used to evaluate the performance of a machine learning model. It's a way to check how well the model will perform on new, unseen data by splitting the dataset into multiple parts and testing the model on each part. Next, why do we need cross-validation? When we train a model, it tends to perform well on the data it's been trained on. However, it might fail when given a new data. That's because it was trained to fit the specific data set and might have memorized it rather than learning general patterns. This is called overfitting, where the model learns the training data too well but doesn't generalize to new situations. Cross-validation helps us avoid overfitting by testing the model on different subsets of data, giving us a more reliable performance estimate. Now, let's talk about how cross-validation works. First, splitting the data. Cross-validation involves splitting your dataset into multiple parts or folds. Think of it like slicing a loaf of bread into smaller pieces. Second, train and test. You train your model on most of these folds but leave one slice out for testing. For example, in four-fold cross-validation, you split the dataset into four parts. You train on three parts and test on the fourth part. Third, repeat the process. For four cross validation, this process is repeated four times, each time using a different part of the data for testing. At the end, your model has been tested on all parts of the dataset. Fourth, average the results. Finally, you take the average of all the test data results. This average gives you more accurate estimate of how well your model performs on unseen data. Now, there are different types of cross-validation, each serving different purposes. Let's take a look at the main ones. First, k-fold cross-validation. In k-fold cross-validation, k refers to the number of parts into which the dataset is divided. The data is split into k equal folds or portions. The model is trained k times with each iteration using a different fold as the testing set and the remaining k minus folds as the training set. This process continues until every fold has been used as a test set once. The final performance of the model is measured at the average of the scores from all k iterations. Second, stratified k-fold. Imagine you are working with imbalanced data like 80% of one class and 20% of another. In stratified k-fold, the dataset is split into k-folds, but the splitting ensures that each fold has approximately the same percentage of each class as the original dataset. This helps maintain the class balance in each fold, preventing issues like one fold having too many examples of one class and not enough of another, which can skew the results. Third, leave one out cross-validation. This is an extreme case of k-fold where k equals the number of data points. In leave one out cross-validation, each data point is treated as its own fold. This means that for every iteration, data point is used as a testing set while the rest of the data set is used for training. This process is repeated for every data point and the final score is the average of all individual iterations. Leave one out cross-validation can give an accurate estimate of model performance, but it can be computationally expensive, especially for large datasets. Now, cross-validation is used in many situations in machine learning, especially first, model selection. If you are comparing multiple models, cross-validation can help you pick the one that performs best overall. Second, hyperparameter tuning. When tuning parameters like depth of trees in decision tree or regularization in regression, Cross-validation ensures the chosen values work well across all subsets of your data, not just the one you initially trained on. Third, small data sets. If you have limited data, cross-validation ensures you can use your entire data set for both training and testing at different times. Now, why should we use cross-validation? Here are the key benefits. First, prevents overfitting. It ensures the model generalizes well to new unseen data. Second, reliable performance metrics. The average results from different folds gives a better picture of how the model will perform in real-world scenarios. Third, effective use of data. Cross-validation uses the entire data set for both training and testing over multiple rounds, which enables the efficient use of data. But like every technique, cross-validation has some limitations too. First, time consuming. If the dataset is large or the model is complex, cross-validation can take a lot of time because the model has to be trained and tested multiple times. Second, computationally expensive. More folds means more computational power is required. Running cross-validation for models like deep neural network can be resource intensive. Third, not suitable for time series data. In basic form, regular cross-validation won't work for time series data as it doesn't respect the time order. Instead, you need a modified version like time series cross-validation. Now let's move on to how you can implement this practically. I will show you how to do it using Python scikit-learn library. First, we are going to import the libraries. Second, we are going to load the dataset. Third, we will define features and target variable. Fourth, we will choose the model and perform cross-validation. And fifth, finally, we will print the result and calculate the average score. So let's open the Colab and do it together. Firstly, we are going to import all the libraries and models. So from sklearn dot model selection import stratified k4 comma leave one out comma cross val scope. Next, from sklearn.ensemble import random forest classifier. Next, from sklearn.datasets import load iris. Run this. Okay, it's done. Now we are going to load our dataset, which is iris1. It is mainly used for classification purpose, and the feature in this dataset represent different flower measurement. So load this. Now assigning x and y values, x for feature variable and y for target variable. Run this. Now import the model. We are using random forest classifier. Okay, now we are first performing k-fold cross-validation. So represent it as score 1. Run this. Okay, now just print the cross-validation score. and print the average score. Now just run this. Okay. So similarly, we can do for stratified and leave one out cross validation. So first do it for stratified. We are giving here n split as 5. It means splitting the data set into 5 parts. Now run this. Similarly, we can copy this to print cross validation score and average, and just change it as score 2 and then run this. Okay, so you can see that for stratified we got our cross validation score and average score. It's nearly same. Now let's do for LOCD, which is leave one out cross validation. Run this. And then run this. Okay, now we will print same cross validation score and average score for this one, which is leave one out. Okay, so you can see here, you can see the number of elements in array is larger as compared to this stratified and k-fold, because in leave one out cross validation we use each data set as a whole. That's why. So here is the practical implementation of different cross validation in a data set. So that's cross validation in a nutshell. It's a powerful technique that helps you evaluate how well your model will perform on unseen data, avoids overfitting, and make sure your model is robust and reliable. From understanding what it is to learning how to implement it, we have covered it all. I hope this video made cross validation easy to understand. If you enjoyed this video, don't forget to like, share, and subscribe for more such interesting machine learning and data science related content. See you in the next one.